right, here we go. This is lesson 8-5. So the first question says, JC and Emma use different functions to model the value of a bike X years after it's purchased. Each function models the data in the table. So we have this table. And obviously, if you guys have heard of like depreciation, I don't know where you would have heard that, maybe in history or social studies, I don't know. When you buy a car, it's worth so much money. The second you drive it off the lot, it's worth less. That's called depreciation. Same thing happens with most things you buy, except for real estate, usually that gains, you like buy a house and it doesn't lose its value the second you buy it. But with cars and bikes and stuff like that, that's what happens. So that's what's happening here. The first year they have the bike, it's worth $500, and just like general like wear and tear on a bike, it's going to be worth less after year 1, and after year 2, after year 3, and after year 4. That's what this is talking about. Both of these girls have different functions. Casey's is negative 14.2x plus 500, and Emma's is 500 times 0.85 raised to the x power. JC's function is a linear function. I know it's linear because it doesn't have an exponent or anything raised to a power. The biggest exponent in it is a 1, and that would be attached to that x, which we never actually say because to the first power just leaves it the exact same. Emma's function is exponential. You know that because she's raising it to the x power. X could be any number. It could be to the 5th power for 5 years. It could be to the 6th power for 6 years. So we know that it's exponential because it's raised to the x power. The first question said, why did JC and Emma not choose a quadratic function to model the data? The reason why this is not quadratic is because this is always going to go down. There's no point where it's going to start going back up. The bike is depreciating in value, which means every year it's going to be worth less. That's never going to turn around after like year 10 and suddenly the bike is worth more money. That doesn't happen. So that's what we're going to write right here is the value of the bike will only go down. It's not going to come back up. And you guys know that we've been graphing parabolas this week. Parabolas, you have like a maximum or a minimum point on it. It starts at a big tall number, goes down, and then goes back up. That's not going to happen here. So you can't model it with a quadratic function unless it goes back up too. So that's the answer to that first question. It says, whose function do you think is a better model, and explain? So at this point, we can kind of use our equations and our calculator to figure out which one actually matches up. So what you would do is you would plug in 0 for x and see what you get. Well, negative 1420 times 0 is 0, and plus 500 would be 500. So she got the right point for 0. If you plug in a 1, it'd be negative 1420 plus 500, and that would give you the exact price that she got for 1 year. You plug in a 2, you're still getting the exact same prices, and you can check all of those. You're changing your x to the whatever year you're wanting. So for 3 years, you'd plug in a 3, and then you'd see what the price was. I want you to try the same thing for Emma's function. Try putting a 1, a 2, a 3, and a 4 and seeing if you get the same answer with the right price for the bike. Someone just try one and tell me. And then tell me what year you get and tell me what you got for the price or the value. I'd type it in, but I don't have a calculator, so. I think you get the right thing for 0. What did you get when you plugged it? Anyone try to plug in a 1 for the exponent? For 1? So if you plug in a 1, you're getting 425, but the value is 485. So is that right? No, whose function is better? JC's is better because at least we're getting the right answers with JC's. All right, so JC's function is better. We'll move on to example 1. It says, how can you determine whether the data in the table can be modeled by a linear function? That's funny that it's a linear function thing because that's what our bell work was today. Here is a table. What you want to do is you want to find, it's almost like you're finding the slope between everything. It's kind of confusing how they wrote it, but how much difference is there from -1 to +1? 2. There's 2 difference. How much difference is there from 1 to 3? How much difference is there from 3 to 5? And from 5 to 7? 2. So all of these have a difference of 2, and then you want to check your other one and make sure they have the same. This is the same. You're adding 1 every time. This one, you're adding 1. This one, you're adding 1. And this one, you're adding 1. So for your x values, they're all going up by 1, and your y values are all going up by 2. So what you'll do, I'm just going to write what they wrote. You subtract your consecutive y values. That's how you figure out the 2. Consecutive means one right after the other. You take the y value before it, and you subtract the one that consecutive. I spelled that wrong. That's supposed to say consecutive, but I messed up, so now it looks like a blob. You take the y before, you subtract the one that comes before it. 7 minus 5 is 2, 5 minus 3 is 2, 3 minus 1 is 2. You get the point. Okay, so a linear function best models the data when first differences are the same. So like we got 2 every single time. That's how you model a linear function. How you write a linear function is f of x equals mx plus b. Same thing as y equals mx plus b, but since we're talking about a function, they change y to f of x. And we've talked about this before. This is definitely on the 8th grade map test. M stands for slope, and b stands for y-intercept. This is like a key concept for 8th grade math, learning how to graph these, learning how to read equations like that, telling me what the slope is, telling me what the y-intercept is, all of that. Now we're on B, so let's move on to that. How can you determine whether the data in the table can be modeled by a quadratic function? So in this case, we're going to take the first differences is finding your y values and subtracting them. So 9 minus 3 is what? 6. 19 minus 9, 10. 33 minus 14, minus 14 is, oh, it's minus 19. I wrote it backwards. It is 14. And then last one is 51 minus 33. And that's 18. So that's your first difference. You're finding your y values. If it were linear, you would get the same thing every single time. But in this case, we got 6, 10, 14, and 18. Now we're going to find our second difference. So we're going to take 10 minus 6. You see, now we're doing these numbers that we just came up with. 10 minus 6 is equal to 4. 14 minus 10 is also equal to 4. 18 minus 14 is equal to 4. So what is the second difference? It's subtracting your consecutive first differences. Consecutive, let's see if I can spell it right this time. The first difference is you're just subtracting your y values. Once you do that, you subtract those. Oops. And you get your second differences. And this time we got the same number every time. A quadratic function best models the data when the second differences are the same. My handwriting is so bad, I'm sorry. So if your first differences are the same, it's linear. If your second differences are the same, it's quadratic. We've been working on quadratic functions this whole time. That's ax squared plus bx plus c. And then the last one we're going to do is how do you know if you can write it as an exponential function? All right, so this is kind of the same situation. We're going to find our first differences. So we would take 2 minus 1. We're taking our y values and subtracting. 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. And then the last first difference would be 16 minus 8. And that is 8. So we have our first differences. They're not the same, so I know it's not linear. Now I'm going to be working on the answers that I just got there. I'm going to take 2 minus 1, and I get 1 again. I'm going to take 4 minus 2, and I get 2. I'm going to take 8 minus 4, and I'm going to get 4. Now we're going to find the ratio of the y values. So we know it is not linear because our first differences were not the same. We know it's not quadratic because our second differences were not the same. So what we're going to do is we're going to take our y values, and now we're going to do like a ratio. We're actually going to divide them. We're going to take 2. Actually, this should go down here. 2 divided by 1. What is 2 divided by 1? What is, and then I'm looking at these numbers back on my y. What's 4 divided by 2? 8 divided by 4. See, I'm looking at my y values, the very beginning things that we did. 2, and 16 divided by 8. So if you know it's not linear, you know it's not quadratic, then you try to do the ratio. If you get the same thing every time, then you know you have an exponential function. So the way you know how to do the ratio, you divide consecutive y values. Obviously, if you figure out that it's linear, do you have to keep going? No, if you know it's linear, it's not going to be quadratic or exponential. But if you figure out it's not linear, then you try quadratic, and then if it's not that, then you would try exponential. So the last one that we are doing is exponential. So an exponential function best models the data when the ratio of consecutive y values is the same or are the same. There's a couple equations we could use for this. The most common one is a times b raised to the x power. But remember, we also have an exponential growth and an exponential decay. So sometimes it looks like this. That's a growth, exponential growth, and then this one would be an exponential decay. So there's 3 different equations it could look like. It's one of those. Okay, so at this point now, we're going to use the information we just learned and we're going to decide which one it is. Like I said, you don't have to do all of them if you know what's going on. Like if it's linear, you don't have to keep going. So we're going to look at our y values right here. I'm going to take -5 minus -2. -5 minus, so if I write that down, -5 minus -2, those two negatives right there actually become a what? So what's -5 plus, that's not a 2, but what's -5 plus 2? -3. Then I would do the next two, -14 minus -5, which is actually -14 plus 5. That is -9. Now I'm looking at -29 and -14. So -29 minus -14 would be -29 plus 14. And lastly, -50 plus 29. -21. So what I can tell you right off the bat is it's not linear, because if it were linear, we would have got the same thing for all of these numbers right here. So I know it's not linear. We're going to do it again, and we're going to see, do we get the same numbers? I'm going to erase all that work I just showed so it doesn't get confusing. That was the first difference. Now we're going to find the second difference. So what is -9 minus -3? -6. -15 minus -9. -21 minus -5. Okay, so now you see that we're getting the same number every time. That means that this is quadratic. If we didn't get the same number, we would keep going and we'd divide our y values and see what happens there. But since we got the same number, you can stop and you know it's quadratic, because that's the second difference. Okay, now we're going to try this one. We're only looking at our y values. What is 12 minus 4? What is 36 minus 12? Close. There you go. 108 minus 36. And 324 minus 108. 216. Close. So we know it's not linear. If it were linear, we know we'd get the same thing every time. We're going to check to see if it's quadratic now. We're going to do the second differences. 216 minus 72 would be 144. 72 minus 24. And 24 minus 8. 16. So we did not get the same number this time, which means it is not quadratic. So now we're going to divide our y values and see what happens. 12 divided by 4. 36 divided by 12. 108 divided by 36. You can see what's happening here. 324 divided by 108 is also 3. So since we got a common ratio, that means that this is exponential. We didn't get a common first difference. We didn't get a common second difference, but when we divided, we did get a common ratio, which means that it's exponential. Okay, we have a couple problems left. These are graphs now, so we're going to decide what we are looking at with a graph. Here it is. The graph shows a population model for 3 cities based on the data over a 5-year period. If the population continues to increase, In the same ways, when will the population of city C exceed the populations of the other two cities? It doesn't tell us what cities we're working with, but it gives us graphs, and all the tables already filled out. Apparently city C is just really growing faster than everything else, and you can see that by the numbers in the graph. These are like steadily increasing, and this one looks like it's an exponential function, like it's increasing much faster than the rest of them. So just looking at the table, city C would have 32, and so would city A. After that, city C is going to increase. So sometime after year 10, you can tell that from the table. We're on year 10. At year 10, city A and city C are equal, and city C is already bigger than city B. So sometime after year 10, C will pass both other cities. We don't have like an exact number. We just know after year 10, we can tell that with our table, it's going to be bigger than both A and B. Also, you can tell that right here where there's this little X. You count it over on your Y value. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is where it's going to cross. So you could tell that from this table as well. And I think that's all they ask us on that question. That's all you have on your notes, right? Okay.